So the most important thing in a Joseon Cook model is to define the material in the right way. So I'm gonna do it with you guys. So let's start finding the Joseon Cook for the steel material. So what I'm gonna put here first is density. I'm choosing for this analysis millimeters and megapascal. So for mass density, I have to put in tons. So it's gonna be like that. Okay. The last thing I will put the elasticity properties, elastic properties. So for Young models for steel, everybody knows is like that. And Poisson ratio is 0.29. Okay, but here comes the thing. For plasticity, I choose plastic, and in the hardening model, I will choose the Joseon Cook. Okay, now these parameters, you have to search for papers in order to get it. In the original Joseon Cook paper has these parameters in a table, so I'm gonna put right here. For A, we're gonna have just a little bit. For A, we're gonna have 792 megapascal. For B, 510 megapascal. For N, coefficient gonna be 0.26. For M, it doesn't really matter in this analysis because we are not choosing to coupling the temperature effects, but I'm gonna put here just for clarification. Melting temperature is I'm using here kelvins, so the melting temperature is like about it doesn't matter too much. The transition temperature is the room temperature, so it's like that. Okay, it doesn't really matter right now. So here's comes the thing. You have to put rate dependent first. Okay, so here you're gonna choosing the strain rate hardening model for our analysis. So we're gonna choose the Joseon Cook. Okay, and the C is gonna be the just a little bit, sorry. C is gonna be 0.014, and my epsilon.0 is the reference, it's the string reference. So for Joseon Cook is 1. So we just defined the plastic properties. We have to also to define the damage model. So we're going to choose Joseon Cook damage. We're going to put the coefficients, the fracture coefficients, D1 to until D5. It's going to be 0, 0, 5. Here comes the thing. The D3 has to be positive because in Abaqus implementation, the code already assumes that the D3 is negative. So you have to put the positive value, the absolute value. For D4 is like that, and D5 is like that. Melting temperature is about Kelvin. Room temperature, strain rate reference again going to be 1. So here's come a good point, an important point. So you have to put here where what is the point that that is that can be characterized as a failure. So uh, in some analysis, so if it is an impact analysis, you can just put 0 here. But in other analysis that you want to check for the stresses, so like in the matching, I will suggest you to follow an article that I'm gonna put here in the video. So in order to illustrate what I want to explain you, I prepared this slide. So what I have here, we have the failure energy method in order to compute the element failure. Abaqus actually calculate the energy in by this formula. So you can see there is an integration from the plastic strain to the failure strain. That is integrated the stress and the yield stress with the length of the element. But this calculation is so much mesh dependent. In Chen article, you're gonna see that is can affect the results really good. So there is another way in order to calculate the GF that is in this way. That depends just on the materials properties, that is the Poisson ratio, the Young modulus, and the fracture toughness that can be on tension or on shear. Of course, it needs more further discussion, but the general idea is like that. And Chen proposed to define the GF in a normalized way. So you divide the GF by the length of the minimal element in your analysis, or the general element length that is going to failure. So here, of course, we can discuss further, but for this video, I think this is enough. So these properties you can find really easily. So I'm gonna put this value in the Abaqus. So okay, now it's done. Okay, so far we have defined the material properties for the Johnson-Cook model. As I said in the beginning, we are not gonna deal with coupling analysis with thermal properties, but of course, if you want to couple the thermal effects, you have to put the conductivity, of course, the inelastic heat fractions. But for this video, I think we must leave this for further discussions.